Hey everybody, this is Larry. This is day 16 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's farm as soon as it loads. Is it my computer? Is it the server having issues? I don't know. No, I mean my other website seems to be loading pretty okay. Am I doing, is it this one? No, I think it is this one actually. Oh, there we go. Just took a while. Oh, but I went to know, okay, this is Monday. I think I have a little bit of whatever, but we'll see how it goes. But basically, I injured myself with respect to, I think I pulled my groin a little bit, running really hard sprinting in softball. I'm gonna give it a couple of days to heal. Today I just kind of went on the treadmill just to a couple of miles just to see if I can fix my form a little bit to be a little bit more precise, a little bit more efficient, a little bit less overusey. We'll see how it goes. But yeah, but no squatting just because it is definitely I use my groin a lot when I squat apparently, so not great. Anyway, yeah, that's my quick update. We'll see how it goes. Today we have 2096, step-by-step direction from a binary tree node to another. So you give a root of a binary tree with n nodes. Each node is uniquely assigned. Find the shortest path. Okay. Okay. I mean, yeah, there are a number of ways you can do it. Honestly, yeah, I'm just trying to think whether there's like a tree specific way of doing it that's like a little bit better, because I think for the most part you know, this is the shortest path kind of situation, with the requiring the path, right? But there's really nothing that special about this, or I don't think there's anything tree specific. Maybe I'm wrong. We'll see what happens afterwards. But I don't think the shortest path, like for in a general graph, I don't think that solution is that tricky. So I think that should be okay. So so the thing is that we're given the value, so which is a little bit annoying to be honest, but not a really big deal. I guess we just have to find the starting, and they're unique, right? Yeah, all the trees are unique. So we just have to do a regular search, and you can do a regular search in any number of way. This is a general binary tree. There's no binary. It's not a binary search tree. There's no structure to exploit. So therefore, we will just kind of do a regular search for the tree, right? So yeah. Then now maybe non-local found is equal to node, something like this, right? And then just find that node dot left, find that node dot right. I mean, this is very, you know, very quick, very basic. Not the cleanest code, but it should be okay. So then here we find, oops. Well, I guess this, fine, that's fine. I don't know. This is very weird, but in any case, yeah. And then now we have found, and then here we can do it in a number of ways. We can use we could use breadth first search. We could use depth first search. I guess that is the one thing that is a little bit different with a tree is that, as we said yesterday, if you watched that video, there's only one unique simple path, which is also the shortest path from between any two nodes. And as a result, it does allow you to do a depth first search, and in theory, I guess that makes it a little bit more flexible in your solution, but I'm still going to stay with breadth first search. So let's get to it, right? Oh, this is a little bit awkward because you have to find the parent node, right? So okay, so then one more thing that we want to do with here, or you could write a second one, maybe it's like connect to parent or something like this, right? I'll separate them out today just because whatever. Construct parent of, oh, and this is not node, this is root, whoops, root none, right? And then your construct parent or connect parent, maybe connect parent is better. Node, and then the parent, right? And then here, if node is none, then we just return. Otherwise, we can say node.parent is equal to parent. This is a very Pythonic thing, but it looks confusing and whatever. But you can also imagine you just have like a parents as a hash table, and then here you have parents sub node is equal to parent, right? So it's not that much. It's just a syntactic thing. It's not that big of a deal in terms of extra space, right? So yeah. So then now you go connect parent node.left node, connect parent node.right node, right? Pretty straightforward so far, right? And then now you have a deck, and then we append the found node. I guess the distance, I don't even think I need a distance. We just need the node, right? Yeah, and then here, I guess maybe that's fine then. And we want to make sure that we have a scene so we don't go to the same nodes. And actually we don't even need to. We say I want to call it parents again, but that is just confusing because I kind of, the reason why I want to call it parents is because now we're trying to construct. So here we have an actual tree, but here what we like this entire thing we have a tree. The input is a tree, but what I want to do is create another tree, which is the shortest path spanning tree, which also has this parent. So in that sense, it's a little bit confusing, but maybe I'll just call it previous, right? Yeah, and then previous of found. Let's just say we store the value because it's unique anyway. Is equal to none, right? So then while length of q is greater than 0, q.pop left. So this is the current node, right? And then we have for next node in node.left, node.right. If next node is not none. Oh, and we'll do node.parent. That's right. But look how easy it is once you kind of set it up. And like I said, if you had used the lookup table, this would have just been parent sub node anyway, or parent sub node. So it's functionally the same, right? If it's not none, then we don't say q dot. Oh, I guess you can't do it this way that easily. I mean, yeah, you can. Okay, fine, right? If it is not none, and previous of and node dot value, this value is not in previous, then we want to append the new node, and then we want to do previous new node dot value is equal to this thing. And I mean, you know, then we could just say that this is the path, and then maybe here we can just add an extra thing, right? And then this would be the P for path. Maybe I just write out path, right? So I mean, overall not a big deal, but it's just a little bit more awkward to look at. Is it up to go parent? Yeah, okay. Yeah, that should be mostly good. If node is equal, node that value is equal to n value or destination value, we break. I think this should be mostly good though, yeah. And then now there is definitely a path from everyone, so we can just say we'll do a path reconstruction, right? And we start from the end, and then we just go back. So we have current is equal to I guess here we should probably keep track of it. So maybe found is kind of weird. So okay, last node is equal to none, right? In this case, then last node is equal to node, and then we break. So then current is equal to last node, and then while current is maybe this is a little bit awkward. We want the path and also maybe the node, just so that it's easier for us to kind of just so that I could be lazier. I think that's the short story, right? So then now while current is not none. Then we do some stuff, right? Then we have previous of current. We have another node and the path, right? Answer, we want to append the path and we'll reverse it later. And then current is equal to node. Yeah, kind of. The reason why I say kind of is because this starts out as none, but I think we can just do like none. Maybe that's fine. Yeah. And then at the end, we want to say we reverse answer, and then I think that should be good. Maybe I'm off by 1. Or some other funky things. Key error. Oh, it's current.value, I think. Okay. I mean, still wrong. What am I wrong by? Oh. I mean, I'm just wrong by being dumb. But, yeah. Hey, hang on. Oh, because I see. Because I checked that current is not none, but this is going to be none, right? So, okay. I mean, it's fine. We'll just reverse it, and then here we we just skip the first element, and that's fine. It's a little bit of a hack, but yeah. All right, let's give it a submit. Hopefully, I didn't miss an edge case, and I didn't, so that's great. And yeah, there we have it, 1568. And I want to say, and sometimes I always forget about this, which is that I didn't really talk about complexity for this problem before now. And it is not because I didn't think about it. I think it's very critical and important in general to think about the complexity before you implement it in general. I mean, like if you're exploring it, then that's another story, but you know what you're doing, right? In general, you definitely want to do the complexity. But for this one, the reason why I didn't talk about it, it's not, I just forgot. Why I didn't talk about it is because I forgot. But the reason why I didn't think about it that deeply is because breadth first search is, the breadth first search is going to be linear, which for a tree is going to be just O of n, right? Because it's O of n nodes and O of n edges, so it's just going to be O of n, and of course these are also going to be O of n. I mean the depth first searches, so O of n in both cases. So yeah, so it's just linear time, linear space, and yeah, and because for linear time, linear space things, I usually don't really give it a second thought unless I knew that the constant it's going to be like some crazy high or at least reasonably high. But for this one, like, breadth first search, depth first search is as straightforward as it gets for the most part, unless you really add a lot of crazy things on it. So that's why I didn't really think about the complexity that much, because it's just going to be fast enough, and it definitely shows. Curious what 3 years ago Larry did, and he basically did the same thing. I mean, I didn't do this this I changed into a for loop, so that's good. Yeah, and here I guess we just kind of I mean, we have the end node and the start node, so I guess that's the thing. Yeah, I mean, oh yeah, no, I had the previous. Okay, yeah, I mean, mostly the same ideas, I suppose. I mean, and like I said, I don't think there's that many crazy things to do it. What are the hints? LCA, okay. I mean, we talked about this yesterday, actually, amusingly, but not today. Oh, I guess that's a cool way of doing it, actually. I think this is actually a good idea. I mean, I didn't do it this way, and I didn't do it this way last time, because it's not necessary, but it is a good idea, because I think for certain problems, this idea is very helpful. But I mean, for this one, it didn't matter as much, but there is definitely problems where that is helpful. So yeah, so the idea here is just to get 2 strings backwards and then just remove the prefix that they share, right? I think that's probably what they're saying. So yeah, yeah, okay, and that would be very straightforward. I mean, okay, let's upsolve this. I mean, now that I have the idea, we can implement this pretty quickly, right? So let's just say yeah, we don't have to write this, right? So we right. So here we have the node and we have the find node. Let's say F for find, right? Turn it. How would I write this? Do I want to do it with breadth first search or depth first search? No, I mean I think this is fine. Okay, fine. And so if node.value is equal to F, then we can it's just it's just annoying, that's all. We can return, if it's none, then we just return none, or just return none. If this is the case, then we can return some empty string, right? And then here, if this is not none, then we return let's walrus this. And also if L is equal to this is not none, then we return this plus L, right? Maybe this is going to end up being L square, I mean N square, or tree, but I just want to see if this idea works, and then we can optimize this a little bit anyway, right? So yeah, so I could do this, and now we can find root start value, string 1, string 2 is equal to find root test value, right? And then we can return. Is there a way to do common prefix? Without like writing something ourselves? No, okay, fine, right? So for I in range of length of min of length of S1 or length of S2, right? So then if S of I is not equal to S2 sub I, then we return this string starting from here. Wait, that's not right. I mean, it's kind of right, but yeah, maybe this is not a great idea. Or like the way that I'm writing is not great. We also forgot to add some stuff. I think this is supposed to be like an L and R, but we don't go up, so it's a little bit awkward. I don't know. Alright, I'm not gonna lie, it's so hot, I'm sweating it. So, alright, I'll leave it to do it next time. So, alright, if I ever do this again, do this the other way. Alright, I'll leave it now. I probably should be able to, I mean, I think the way that I would want to do this is just by breadth first search, and yeah. Because then you want to way to connect them. I think the way to connect them is just from S1 to the LCA, and then LCA to the thing. So you chop off the prefix, and then you do some reversing it. But I guess it's just a lot of if statements, and I'm lazy today. Sorry, friends. I maybe this is an upsell for you at home. I am very sweaty, and I need to take a shower. So yeah, that's all I have for today. Thanks for watching. Let me go back to the other code. Okay, fine. Let me go back to the other code so you can kind of take a look at it. But yeah, here's my finding node for finding the starting value. I connect the parents here, though you could really have done it in the same function if you really wanted to. And this is just a very standard breadth first search for shortest path to create the shortest path spanning tree. Is a tree in that this is an upward edge to the previous, and yeah, and then you just reconstruct the path. That's all I have for today. Let me know what you think. Thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.